Let us now define some of the cosmological parameters which are used to characterize different cosmological models. The first of them is the Hubble constant, or more accurately, Hubble parameter, because it's not constant, it changes in time. It is defined as the ratio of the time derivative of the scale factor by the scale factor itself, the normalized slope of r of t curve. Today, its value is roughly 100 kilometers per second per megaparsec. Remember, this is the slope of the Hubble diagram, which plots velocity versus distance, thus the units. Since it's length over time in the numerator and length in denominator, its dimensions are 1 over time. Essentially, Hubble constant gives the scale of the universe. It's a slope at a given time, and therefore, when you draw a tangent on r of t curve, its intercept on the time axis gives you inverse of the slope, which is 1 over Hubble constant, which is also known as the Hubble time. And that's roughly some 10 billion years or so in modern cosmological models. This is close to, but does not have to be equal to, the age of the universe at that time, t0. If you multiply Hubble time by the speed of light, which is length over time, then you get a Hubble length. The next one is the density parameter. It characterizes the mean density of the universe at any given time. If you look at the Friedmann equation, assuming that cosmological constant lambda is equal to 0, the universe is flat if it has the curvature constant of 0, and that can be also expressed as the critical density over 3 times h0 squared divided by 8 pi g. Note that the critical density is determined just by the Hubble constant at that time. The ratio of the actual density of the universe to this value gives the omega matter the density parameter. If the density is exactly equal to critical, then omega matter is 1 and universe is flat. The next would be the dark energy density parameter. Just like mass has a mean density, so would the energy, and we know that from observations now that actually universe does have a mean energy density. It is defined from the cosmological constant according to this formula, and the total matter energy density would be then simply a sum of the energy density of the matter and energy density of the vacuum. We also define the deceleration parameter, often designated with lowercase q or q0 at the present, which in the absence of cosmological constant reduces to 1/2 of the density parameter. But if the cosmological constant is present, its value is different. So this is what cosmological parameters do. Hubble's constant gives the overall scale of the universe, temporal and spatial. It does not depend on the density of the universe, cosmological constant, or anything else. The other parameters, omega matter, omega vacuum, and so on, determine the shape of the r of t curves and do not depend on Hubble's constant. Therefore, their measurements will be really done in a different way and completely independent. You can determine scale of the universe without knowing what its density or whether it has dark energy or not. Conversely, you can find out the mix of the densities in the universe without knowing accurately its overall scale. This is done through cosmological tests, which we will describe later. So let's have a few notes here. Hubble parameter is often or always called Hubble constant, and it's sometimes written in the following normalized form. We divide actual value of Hubble constant, which is usually expressed in kilometers per second per megaparsec, by 100, and that is denoted with lowercase h, normalized Hubble constant. Then you can scale for other values of the Hubble constant as you wish. Sometimes it's divided by 70, which is actually very close to its present value, and that's denoted as little h with the subscript 70. And that is Hubble constant in units of 70 kilometers per second per megaparsec. The current value of the critical density, which is determined entirely by the value of the Hubble constant, is approximately 10 to the minus 29 grams per cubic centimeter, including both matter and energy. So we can write density parameters in the following form, that omega of the matter, omega of the energy density or vacuum, plus omega curvature all add up to 1. Omega curvature really is defined simply as a deviation of the other two from unity, but it makes a more elegant formula in this way. So now, when we look at the definitions of these parameters, as shown here, we can plug those in Friedmann's equation. And here is the Friedmann equation expressed through cosmological parameters. As you can see on the left, its value of Hubble constant and other parameters participate in the equation. All right, now next time we will actually try to solve Friedmann equation and actually reach the cosmological models.